In this recording, we're going to look at some special types of linear systems, some ones that have some unusual sorts of solutions. So first off, let's graph this system to show that it has no solution. I'm not sure if you have a mental image of what that might look like. Maybe you do. But let's get both of these in a graphable form. So pause and play the recording when you've got both of these in y equals mx plus b form. Okay, so hopefully for this top one, you subtracted 2x from both sides. But these are not like terms. They stay separate. For the bottom equation, similar, took away 2x from both sides. All right, again, not like terms. Let's graph them. Good little review of how we graph, right? So the blue one, do it in a blue pen. Your slope and your y-intercept. So see if you can put that on the graph. Play the recording when you're ready. Okay, so hopefully you went up to 5 on the y. That's our y-intercept. Slope is -2, so from that point I'm going down 2, right 1. Plot a series of points till I run out of space. And do the same in the opposite direction. Alright, so I'd like you to do the same for the red line. Play the recording when you're ready. Hopefully you plotted a y-intercept of 1, same slope, -2. And now we can make lines. Grab your pencil. Grab your ruler. We always label, in case of the blue one. If you forgot which one is which, you can always check by the y-intercept, right? That's the distinguishing characteristic. They have the same slopes. Hopefully you thought of a special mathy word for lines that have the same slope, but different y-intercepts. I'll give you 5 seconds to think about it. Okay, if you haven't thought of it, you got to pause. You got to rack your brain. You got to Google. You got to do something. All right, and the word is parallel. Okay, these lines are parallel. They'll never touch. They have the same slope, but different y-intercepts. Therefore, right, they have no solution. They have no intersection point, right? No intersection point. That was the point there. All right, so it says these are pretty similar looking system, right? Same system. Use the substitution method to show that it has no solution. So good little review of substitution. Get as far as you can, then play the recording when you're ready. Okay, so hopefully you worked that out. I'm going to take that top equation, get a variable by itself. It's going to be easier for me to get the y by itself. Take away 2x from both sides, so I've got -2x plus 5. Then what I'm going to do is substitute what y is equal to into the y of the second equation. So I'm going to start to write out the bottom equation. All right. And as I write out that bottom equation, when I see a y, I'm going to substitute what y is equal to. And then the rest of the equation. So it's the same equation. I've just changed that y out for something it's equal to. I'm allowed to do that in math. All right, because there's nothing to distribute, those parentheses really don't matter, so I can essentially rewrite it like this. 2x minus 2x. Those are gone, right? But 5 doesn't equal 1. So that would mean no solution. All right, and that's what it looks like algebraically. You're going to end up with something that can never be true. With a graph, you're going to end up with parallel lines. Okay. On the flip side, we've got a system with an infinite number of solutions. Let's talk about what that would look like graphically. Okay, so let's try to get both of these into y equals form so you can graph them, so you can see their slope and y-intercept. Play the recording when you're ready. Hopefully you did this. I will add 2x to both sides. Second equation. first thing I'll do is add 4x to both sides. But I don't quite have y equals yet. I don't have y isolated, so I'll divide all the terms by the coefficient of y. Now I've got the two equations. Go ahead and make their graphs, play the recording when you're ready. Okay, so hopefully this is starting to come back to you, right? Making graphs. Green one, I've got a slope of 2x plus, or slope of 2, y-intercept of 3, up to the positive slope this time, right? Go ahead and make that line. Now the thing is about the second equation, it's the same line, right? I'm still going to have the same y-intercept if I plot that, and the same up 2 over 1. I'm going to have the same exact line. So if the line is on top of the other line, that means infinitely many points are solutions, are intersection points, right? That's what that looks like. Well, let's see what it would look like graphically. Algebraically. Well, I could use linear combinations or substitution. Well, I just did substitution in the other one, so I think linear combinations will be the one for me here. What could I do? I could either get the x's to be opposite or the y's. Doesn't really matter, it's up to you. You're thinking x's? Okay, well, we'll do that then. Let's multiply the x's by a -2. Okay, so I'll distribute a -2 to the left side because I want the x's to have opposite coefficients. I want to have a positive 4x and a negative 4x. So I've got a positive 4x when I distribute here and a -2y. Over on the right side, I've got -6. The bottom equation, I'm going to leave right as it is because it already has the opposite coefficient for the x's. And now I'm going to add because I want to eliminate the variable. So when I do that, the x's add to 0. So do the y's. So essentially I've got 0 on the left. And the right side equals 0. So when 0 equals 0, that's true for all values of x and y, or at least many values of x and y, I should say. Right? So if there's infinitely many solutions, that's when you have eliminated all your x's and y's, but you have a true statement. The bottom part we will work on in class, trying to figure out whether there are 0, 1, or infinitely many solutions. Thanks for watching.